So please start. Yeah.
Okay. Good evening, everyone. So I think I see. So Harit, Himanshu, Vivek are think students. Padma Priya is from NPTEL team, I think, right?
Yes, sir. Yeah.
Okay, sure. So I looked at the form that was circulated and I couldn't find any questions that were asked over there. So there are questions we could just discuss. You could ask right here and like unmute yourself and ask, and we could discuss. No questions?
Good evening, sir.
Good evening, Vivek.
Yes, I have a question, sir. In Rasberov proof, we have used this field F3.
Okay.
So, is there anything special about F3, or is it the case that it is that the proof holds for any finite field, maybe?
The only speciality of F3 is that, or that we are using, is that F3 is not the same as F2 in the sense that it has characteristic 3 versus 2. So if we had used F5, it would have worked. 7, it would have worked. In fact, I say this in one of the lectures. Let me just pull up the notes. That the same proof. So basically, parity is like you're like it's an F2 thing, right? So at the end of the, I think lecture 42, I say that like you cannot have a mod P gate. So mod P is like that P is any prime. So parity is like you're testing whether the numbers add up to like are they even or not, right? Mod 2 or not. Using using an AC0 circuit. So in fact, even if we use mod 3 gates, even then we cannot get. That's what we are actually showing. So not just not and or. Even if we use mod 3 gates, we cannot do that. So what this, so maybe I'll just project my screen. Just hold on. Find the project. Share screen. Okay. Are you able to see the screen?
Yes, sir.
Okay, so the proof actually shows that this is part of the notes that is anyway available. Parity is not in AC0 with like square bracket 3, which means that in addition to and, or, and not gates, we are also using mod 3 gates. Mod 3 gates is something which evaluates 0 if and only if the number of bonds is a multiple of 3. Right. So this is what we actually show. So because obviously if we allow mod 2 gates, then it is trivial, right? Because what we are computing is mod 2.
Yes, sir.
So the only thing that we are using F3 is something that is of not characteristic 2. So the same proof works to show that mod P cannot be computed using AC0 and Q. So where this means that in addition to and, not, and or gates, you are allowed mod Q gates. In such a situation, you cannot compute mod P, where P and Q are different primes. So yes, different primes. So P is not a multiple of Q or whatever. So this is the only reason why F3 is used. Yeah.
Yes.
Something that is not characteristic 3.
Yes.
So who was it? You who asked that question that I responded to earlier, like today? No, that was some other student.
Yes.
Yeah. So far we have seen just sharing in general. We have seen so this is week 8 going on, I think, right, or week 9 going on. This week 9 going on, I think. Yeah, so far we have seen time complexity, space complexity, randomized computation, circuit computation, right? Now, the rest of the topics that are going to come are kind of slightly more advanced topics. Even this parity not in AC0 is like that. So we will see things like counting, the complexity of counting. What is Sharpie? Sharpie is I'm just saying in the upcoming weeks, and then we will see interactive proofs, and we will see communication complexity. So some of these are somewhat or you could say that these are kind of discretionary topics. Like if you look at different courses on complexity theory, some may include this, some may include some other topic in place of this. Yeah.
So, sir, in this Rasberov's proof, what exactly we have shown that this is a lower bound for parity?
Yes. So basically, parity cannot be computed using an AC0 circuit. And even if we allow this mod 3 gates, so lower bound in the sense that it's an impossibility result. You cannot compute parity with this kind of setup. AC0 means polynomial size, constant depth, and unbounded fan, right?
So, sir, at the beginning of the lecture, you say that it's hard to prove lower bounds because
in general, yes, in general,
so
it is hard to prove lower bounds.
Yeah, because we have to account for all possibilities.
Correct.
So, how in this proof they have accounted for all the possibilities?
So we have seen a couple of proofs already. So I'm just talking in general, not specific things. Like for instance, we first saw SAT is NP complete, right? So
yes, sir.
Right. So there the challenge was that any language in NP one has to reduce to SAT. So now, how do you show that every language reduces to SAT? So we construct something in general and then showed that this general NP language reduces. So something similar is happening here, right? So what is happening here? So we choose, my machine is a bit slow. So we choose a general general function which can be computed by AC0. So I say this in the lecture. So this is all introductory part. So we say it like this, right? Every just hold on. I'm sorry. Are you still able to see my screen?
No, sir.
Oh, okay. I think I accidentally pressed close button. Okay. So we say that, let me just minimize this zoom window. So we say that every AC0 function can be approximated by a low degree polynomial. And this is mostly the first lecture 41, right? How do we do that? We first show that, so the notion of approximation itself needs to be defined, right? So a random polynomial that is chosen from a distribution can approximate, epsilon approximate a function if for any value of x, right, the polynomial matches the function with probability at least 1 minus epsilon, or the probability of not matching is at most epsilon. So this we define, and then we show how to, if the function is created using an AC0 circuit or a circuit with constant depth using and or and not gates, how we can compose this, and we can bound the error. So basically what we are doing all over here, like we showed or so we get this thing that any function that can be computed by a circuit of size S and depth D can be approximated by a fixed polynomial, or approximated by a distribution, and then we move to the fixed polynomial. Then we infer that if there is a distribution, there's also a fixed polynomial, such that the degree is bounded, right? So degree is log S to the power D. So in an AC0 circuit, depth is constant, size is polynomial, so log S is also constant, right? So degree is bounded. And then we show that, so this is the proof of that. This is a proof that if there is a distribution, you can also get a fixed polynomial, right? So, and then we show in the next lecture, right? Then we show in the next lecture that this is not possible. Any polynomial in this F3 that for which 1/4 approximates parity should have square root n divided by 10 degree. So this is the high level picture of the proof. So first we show that any function that can be represented by a circuit of fixed size and depth, you can get a fixed polynomial such that the probability, okay, here the probability is chosen over input, right? So from the distribution we move to the input. We show that the probability that the polynomial matches the function is at least 3/4, and then we show that for parity, the degree is at least square root n by 10, but here the degree is O log S to the power D, right? So these two, now if you have to match these two things, so this says that any such polynomial has to be of degree square root n by 10, which now if you fit square root n by 10 here, what we are getting is that O log S whole power D is greater than square root n by 10. And I will run the math here, which gives you that the size should be at least to power this thing, which is not polynomial size.
Yes.
So this is the high level picture.
Yes.
Yeah. Any other questions? I'm happy to see many participants today. Yeah, I see around 7-8 people.
Sir, in the proof of Cook-Levin theorem,
Okay.
we have used the non-deterministic Turing machine.
Right.
So is it possible that we can use the verifier-based definition and still do the proof?
It is more or less the same thing, right? Because we assume, okay, let me just think. So what do? What did we do? I think it was in week 2, I think. Week
Yes.
1.
So we had that computation tableau.
We had the computation tableau, and we can do the proof in that manner as well. I'm just trying to see what proof we did. Okay, so we did in this manner, like the input is given.
Yes.
And then the non-determinism manifests in terms of different computation paths possible. We can do it in the other way also. It's like you can. Then we'll have to allocate some space for the certificate string, and then the calculation will be deterministic, but it will be pretty much similar. We are not going to gain any new insights from there. We can do the proof in that manner as well. Yeah. In fact, one proof could be like, once we have all this, you can build a circuit basically which does this calculation, right? You can build a circuit, a small circuit that looks at three positions and gives the next row. And the circuit is just repeated over and over and over again. Right? This is a determinist. It's a circuit that takes these three positions and outputs this. And then you can just build a whole circuit for this and then say that this circuit gives you the final output, whether it is 0 or 1, accept or reject. So this is,
yes.
Yeah. So there is such a proof as well. Yeah.
Yes. So while studying this BPP, I saw that BPP is a semantic class. So
Okay.
what is the meaning? I mean, they write that checking a probabilistic machine is an undecidable problem. So, what is a semantic class, sir?
So in fact, this I touch upon in week 9, I think, lecture 47 and 48. We probably haven't reached till there, right? Or we are in week 9 now, is it?
Yes, sir.
Yeah. So anyway, so I'll tell you what it is. Semantic means, see, given a Turing machine, now let's say deterministic Turing machine, okay? It either accepts a string or does not accept a string, right?
Yes.
So there is a clear-cut language associated with this Turing machine. We know what is what are the strings accepted by this, and these 6 strings that are accepted by this give rise to a language. Non-deterministic Turing machine also, yes, right? It gives rise to a language. But if it's a probabilistic Turing machine, and now let's say we are defining BPP as so we are looking at a BPP language. Okay, so we are saying that now I want to look at. I will say that all the strings that are accepted with probability at least 2/3, right? Because it's a probabilistic Turing machine. It may get accepted sometimes, it may not get accepted sometimes, right? So there is a probability associated with each input string. So you can say things. So now let's say I define a string to be accepting if it is accepted by at least 2/3 with probability at least 2/3. I will say that a string is rejecting if it is accepted with probability less than or equal to 1/3. Right? This is the BPP definition, right?
Yes, sir.
But then there could be strings that are accepted with probability 0.4 or 0.55, something like that, right? So now where do you put them? So now, given a probabilistic Turing machine, it's not clear what is the language associated with this Turing machine, simply because ideally I want a language to be either accepted with probability at least 2/3 or at most 1/3. I don't want this gap. So given a probabilistic Turing machine, it may not be associated with a language in this manner. This is what is called a syntactic class. So BPP is not a syntactic class. So that's why it's called a semantic class. Because given a Turing machine or even a probabilistic Turing machine, it's not clear whether there is a language associated with this. So this is not, but whereas in a deterministic polynomial time Turing machine, there is a clear language associated with it. Either it accepts or it does not accept, right? And not deterministic Turing machine also, either it accepts, does not accept. Whereas semantic class means given a Turing machine, there is no, it's not obvious whether it leads to a language or not. That is what I mean by syntactic versus semantic classes. Is that clear?
Yes, sir.
So in addition to it being a probabilistic machine, we wanted to satisfy some other property so that we can say it accepts this language or it recognizes this language, right? So that also leads to this definition of promise problems, where we talk about giving an input with a promise. So where we say that given an input, it either satisfies property X or usually it satisfies property no. And then we just have to decide either does it satisfy yes or property yes or property no. And there may be things in between which we don't care. Right?
Yes.
Yeah. So this is the promise problem. So the problem comes with a promise. So I may give you a graph and say that either it has a clique of size 20 or all the cliques are of size less than 5. You tell me which of these is the case. This is a promise problem. I'm giving you a graph. Either it has a large clique or all the cliques are very small. So if the given graph, the largest clique is of size 10, I don't care. I have broken my promise and I don't care what you respond. As long as I stick to my promise that either the clique is large or all the cliques are small. In that case, you have to tell me which of these cases it is. This is what is called a promise problem. And yeah, so this is not really answering the semantic versus syntactic, but this discussion leads to that discussion. So I just thought I'll just say it again.
Yes. So, sir, in case of probabilistic computation, so we saw that that inverse polynomial, it was we get benefits only when we have that inverse polynomial relation. So,
Okay.
is that a promise kind of?
No, I'm not getting. So the BPP itself is a promise, right? So I define. So given a machine, I have to given a machine that recognizes, like I want some gap to be there, right? So if you want to make a BPP machine for a certain language, you will want to accept all the strings. You will say that all the strings in the language have to be accepted with probability at least 2/3 or 0.6 or something, and rejected with or all the no strings you want to be accepted with probability at most 0.4 or something like that. So you want that gap to be there.
Actually, sir, I was talking about the first example that you gave while starting the lecture on probabilistic complexity classes.
Okay.
So you gave the example of that AND function, and exactly one instance was true. So the probability was 1 divided by 2 to the power n. So, so instead of that, you said that if we have the inverse polynomial relation, so 1 by some px.
Correct.
So there we get benefits out of randomized computation.
Correct.
So
yes.
I was trying to understand, is this a promise that in case of BPP, the number of instances has to be polynomial something?
No, that was just a motivating example. In BPP, I'm not really that is not a promise. A promise problem means you are given a problem with a promise. So one example is what I just said. You tell that I could give you like with the clique, either there's a huge clique or the clique is very small. So now you have to determine which of these two is the case. And if it is falling in between, there is no huge clique also. There are some medium-sized cliques, which so if it falls into the don't care zone, I don't care what you respond. So basically, it is like I'm giving you some, or I'm giving some leeway. Like if it falls in the in-between zone, I do not care what the response is. So
Yes.
this is not the same as what I said at the beginning of this introduction of randomized computation.
Yes.
Yeah. Any other questions?
Sir, in the lectures, actually, I was trying to understand this NC. You said that NC is represents those parallel algorithms, parallel computation. But actually, the relation was not very clear to me. How NC relates to parallel computation, sir?
So, in the sense that there are multiple, like usually NC means you can think of each gate as a processor, or each collection of gates as a processor, and it is usually thought of as an equivalent of parallel computation, because the depth is small. You are saying small, like polylog depth, right? And if you have lots of inputs, like, and each gate computes independent of the other gates, right? So that the NC is thought of as an input, as a so that is all there is to it, not much more. Like, you can think of it as like there are many inputs and each gate computes independent of other inputs, right? So that's all. So in the sense that this is computing in parallel with other things.
Oh, okay.
And typically the depth is small, right? Polylog depth.
Yes, sir.
Anyone else has any question? I think it's so far only Vivek has been asking, I think.
Sir, I have one more question about this non-uniformity.
Okay, sure.
So, what I understand that we have the language and we can slice the languages into inputs of different lengths. So that's the idea of non-uniformity.
Right.
And so,
And you can do different things with these different lengths. That is what happens, right? That's why it's non-uniform.
yes, sir. So, sir, in case, let us say we have this Turing machine model, and for each input length, we restrict the number of tapes that can be used. So, for example, length n, so only n tapes we can use, and so on. So, would that count as non-uniformity?
Not really, right? So because I think I don't think we do it in our course, in this course, but maybe in the theory of computation you would have seen that if any number of tapes, you can have an equivalent machine with a one tape machine. The running time will just go up into by quadratic factor or something.
Oh, no, sir, not number of tapes. I'm telling the number of cells on a single tape. So, for example, if the length is 5, I restrict the Turing machine only with 5 cells.
No. Then if you are, so are you saying that there will be only finite amount of memory available?
Yes, sir. Yes, sir.
No, this is even worse, because what will happen is that if you have only finite number of memory available, then you can actually show that the Turing machine is equivalent to a DFA, because like each cell can take only 2, or let's say some fixed number of values, right? Let's say you have 10 symbols, each cell can be take only 10 symbols. So then you can show equivalence to a deterministic finite automata, in which case the language that you can deal with is only regular languages. So
yes.
this is the correct, the appropriate parallel is the Turing machines that take advice, right? So basically with each input length, you can do something different. So this something different, so that is why you first of all you have to have a circuit family, because each circuit has a fixed input size. But then the non-uniformity comes from the fact that each circuit can do something completely different. Like, there's no clear way of, let's say there is one circuit here in this in the screen. Now, if I get like which is taking 1, 2, I don't know, some number of inputs, right? 2n number of inputs, I think. Right. So now the question is that now if I have like, how do I generalize it to 2n plus 1 inputs? It's not very clear, right? So each circuit can do things quite differently, right? So this is, and that is where the non-uniformity comes in. And in the case of Turing machines that take advice, this non-uniformity, what we say is you allow one advice string for each input length, and this non-uniformity can be built into this advice string. So this non-uniformity could be saying the circuit for this n or looks like this, right? I think that is one direction of the proof. If there is a Turing machine that takes advice, then, or if there is a circuit family, then you can get a Turing machine that takes advice, basically by encoding the circuit family in the advice string.
Yes, sir.
Yeah.
Yes.
Okay, there are other students who are attending are Harith, Himanshu, Susrut, and Vijay. Do you have any questions? I'm glad to see that at least even the extent of activity in the forum, it's good. There are enough questions and there are people who are asking questions, and I'm happy that people are following. Like even things like parities, not an AZ0. It's kind of a long proof, right? So today's question that I forget who asked about one small one observation, which was a correct observation, that the proof assumed something which was not there, which that assumption should not have been there. That is a very thoughtful, or somebody, it showed that the student followed the proof well. There are no other questions, then we can close this session. Okay, then thanks all for joining. Yeah, hope to see you in maybe sometime in another couple of weeks or so. Karthik, we can close the session. Karthik?